Hi everyone, the next topic is diagnostic plots. The linear model have several assumptions such as y and x have linear relationship, or epsilon is IID and normal. We want to check these assumptions by using some plots. And also, we want to check if a few observations affects too much to determine the regression line. So if a few observations affects the regression line too much, that is not good because the estimation is not very robust. So think about this figure. So we have 6 observations. Just ignore this one. If we have the 6 blue observations here, then regression line is this slope. But actually this regression line is influenced a lot by this observation, only just this observation. Because this observation moves to here, actually regression line changes dramatically and we get this regression line. So this happens because these observations are distant from other observations. So these are located far right. So we have to transform this x, for example, by square root. Then these large observations get closer to the other observations. And now the no observation makes too much contribution to determine the regression line. So we have to check if this situation happens or not. So we will discuss the 4 plots. One is residual versus fitted plot. So this will check if linear relationship between x, y, and y is correct. And the second plot is normal QQ plot. So this will check if errors are normally distributed. And the third one, scale and location plot, we will check if any transformation of x and y is necessary. And the last one, residual versus leverage, we will see if a few points are too influential in regression. So these plots are obtained by these 4 codes: plot of linear model object, then option equal to 1, 2, 3, 5. Or if you type plot of L mod, you can see these 4 figures one by one. But to save files, you have to use these commands. Okay, so first we think about the residuals versus fitted. We will check if the x and y have linear relationship. Okay, so we have fitted here, but basic idea is that we compare y with xi. So if the relationship between xi and y is not linear, then we should have some distinctive pattern in residual plot. For example, in this case, x and y have some quadratic relationship. So in this case, if we make a fitted line here, residuals have distinctive pattern. This is positive, this is around 0, negative, negative, positive, large positive. So even if we just plot residual plot versus xi, we have distinctive the U-shaped pattern. Like this. Okay. So if we found this kind of pattern, you have to add some variable or you have to do some transformation. Okay, and residual versus fitted graph is very similar because fitted values is equal to beta naught hat plus beta 1 hat x if we only have one predictor. And if we only have one predictor and we just ignore this constant term, basically fitted value is variable x, just linear function of x. So we can detect this kind of pattern we mentioned in this residual plot. If we have more than one predictors, actually fitted values meaning is a little vague and we don't know that what kind of pattern will be detected between fitted values and residuals. But since R does not want to create all the pairwise, all pair of Y and Xi, so they put just residual and fitted. So the best way to see what's happening is to make this Y versus Xi, or either Y or residual, the epsilon hat versus Xi for each Xi. Okay, so the second one, second diagnostic plot is normal QQ plot. Normal QQ plot will see if residuals are distributed normal. And this is actual residual. It's standardized version, but basically actual residuals. And this is theoretical quantile. So if actual residuals exactly follow normal distribution, all points are on this diagonal line, y is equal to x. But if some discrepancy is detected, such as here and here, that means observations are not normal. So in this case, some standard residuals are much larger than theoretical quantile. So that means we have heavy tail on the right-hand side. So it's not exactly normal. We have some extremely large observations, heavy tail. And here, we don't really have large negative residuals. So probably this is a little shorter tail. So this kind of distribution of epsilon hat is detected. Okay, so here, this is not just residual, but the standardized residual. So I will explain next what is standardized residuals. Okay, so idea is here. The observations on the far left or right side influence to the regression coefficients more than other observations. So think about this example. So we have 6 observations here. So 1 observation here, and 1, 2, 3, 4, and 6. And suppose this blue line is the true regression line. So the first observation here and the last observation here, so these have large errors. But if we estimate the regression line, estimated regression line becomes this. Because this line is influenced a lot by this observation and this observation. So in this case, epsilon hat becomes artificially small because originally epsilons are large, but the epsilon hat is very small because this observation itself affects this regression line. So in this way, you can recognize that epsilon hat tends to be smaller when x goes to most left-hand side or right-hand side. So we have to adjust that term. So if original observation is epsilon j hat, we have to divide some constant. If the observation xi is on the right end or left end, we have to divide this by smaller number to make this adjusted, the standardized residual a little larger. So hj is basically a constant that is large if xi is away from the center. Center of x. So xij is away from the xi. Maybe I will say xi bar. So how to get hj? So hj is actually the jj's component of matrix H, and H is this matrix X times X transpose X inverse X transpose. And actually this matrix appears when we get x beta hat. X beta hat is x times x transpose x inverse x transpose y. So that becomes actually hy. So you can imagine why h is used in the formula of this standardized residual. So y hat is equal to x beta hat plus epsilon hat. And epsilon hat is y hat minus x beta hat. So that is actually y is observed. So this is y. So this is y minus x beta hat. And this is actually I minus h y. So to evaluate epsilon hat, size of epsilon hat, this I minus h matters. So this is the definition of standardized residuals. So it's slightly different from usual residuals. Okay, now the third plot. The third plot basically see if we need some transformation in y especially. And this y-axis is standardized residual. Actually take square root, take absolute value and square root. And this is fitted value. So actually, if we need transformation for y, that we have maybe larger observations at larger fitted values. So the graph looks like this. So this happens when we need transformation in y. So think about the case to explain the situation why this kind of figure happens when y is not transformed appropriately. We think about one example that the x is true weight of some animals and y is measured weight by some scale. Then suppose x is, okay, 1 kilogram, 10 kilogram, 100 kilogram, 1000 kilogram. Then measured weight may be 1.05 or 9.5 or 104 or 900, maybe 60 or something. Okay, so think about the usual, just the simplest case that the true model is y is equal to x plus epsilon. What's the size of epsilon? Size of epsilon is 0.5, 0.05, and 0.5, and 4, and 40. So this is natural because when x is large, actually the error gets larger. If we measure the weight of larger animals, that we may have larger errors. So if this case happens, actually larger fitted value, that means larger x, that we have larger residuals. So in this case, usually we have to take logarithm. So true weight and measured weight. The measured weight is the true weight plus some percentage of true weight. Okay, so error is proportional to the size of x. So in this case, that we need transformation of possibly both x and y, sometimes only y. So we may fit log of y on log of x. So this figure can detect such pattern. But in this case, actually, we don't really see any, we don't need transformation between x and y. So last one is influential points. So if a few observations are too influential, it's not really good. And if residual is large, of course, influence is large. So think about the situation that some observation have large residuals, then such point is influential. For example, that we have these observations, but we have one observation around here. Then this is slightly larger than the center of X. So if the true regression line is like this, if we have this observation, maybe regression line is affected by this observation. So size of the standardized residuals is important. So larger standard residuals, that we have larger influence, maybe around here, and also maybe we don't have many observations, but just the lower side. So around 0, we don't have much influence. But at the same time, we have to care about leverage. So leverage basically means a kind of function of distance from the center. Okay, so these observations don't have a large standard residuals, but these are influential because these are on the right-hand side or left-hand side. So if leverage is larger and the standard deviation is larger in absolute value, then such observation is very influential. So in this case, it's not really bad, but these observations are slightly more influential than the others. If some observations are here or here or here, or even here, so these observations are very influential. Because these observations are near the right end or left end, and also error size is very large. And the other way around is true. If this is large negative value, such as around here, so these points have also very large impact on the regression line. Here, leverage is basically represents the distance from the center. So farther away the points are, the larger the leverages are. But here, we have, we don't have the formula here, but the textbook discusses the formula. And here, we have some contour plot for so-called Cook's distance. You can see that here, the 1 and negative 1 and 0.5, and we will have the similar line this side, also maybe 0.5 and 1. And these are contour plot for Cook's distance. So basically, the larger the Cook's distance is, then that point have more influence on the regression line. And Cook's distance is defined by this quantity dj, d sub j. And d sub j is defined by using y hat and y hat subscript j. So y hat subscript j is what? Actually, this measures the impact of j's observation, xj, yj. And actually, this y hat is calculated in the same way as y hat, but we don't use the j's observation to get the regression line. So in that way, that we can see the impact of xj. We estimate y hat with xj, and we estimate y hat without xj. Then basically we take the all sum of the discrepancies squared and divide by some normalizer. And actually this is just the monotone function of hi. So hi gets larger, then di get larger. So that means the observations are further away from the center of X, then we have the higher d sub j value. So these are diagnostic plots for linear regression.